Have you ever planned to do something in the morning after the sun comes up? Let's say you want to go do something out on the lawn, or you want to go play a round of golf or something like that, play a game, sporting event out on the lawn or on the yard. And you get out there, all of a sudden the grass is your feet just get totally wet, soaking wet, um, due to the dew on the grass. Well, that's the dew point. And so what I'd like to do is show you how to determine what is the dew point for atmospheric air. So let's get started. This is the second video on making calculations associated with psychrometrics. In other words, mixtures of dry air and water vapor of the atmosphere around us. Very common calculations that mechanical engineers need to do. And so here's just an illustration of maybe you want to go play a round of golf, for example, in the morning. Here's what we'll cover is just some of the basics about what is the dew point? What does the dew point mean? And then finally, we'll show you a worked out example problem for determining the dew point temperature for outside air. Okay, how cool does it need to get for dew to form on the grass? You're going to be able to determine that, and that's called the dew point temperature. Typically in summer, in early fall, in spring, we tend to observe that it gets cool at night and gets cooler and cooler and cooler at night. And in the morning we go outside and we see water water droplets all formed on the grass. Well, that means that overnight the temperature of the atmosphere has cooled below the dew point temperature. Okay, and so what does that mean technically? It means that the partial pressure of the vapor in the air has reached the saturation pressure of the vapor at the cooler temperature, and that's called the dew point temperature. And when we continue to cool just a little bit below that dew point, that's when the vapor condenses out of the air vapor mixture and the condensate forms on the blades of grass that are a little bit colder than the atmosphere. Real quick look at the TS diagram. Now, this is the TS diagram for the water vapor only contained in the atmospheric air. We're not looking at the dry air. We're looking only at the water vapor. And this would be our initial point. This would be in the evening before the atmosphere starts to cool down at night. So we're going to be at some relative humidity phi, less than 100%. Okay. And then overnight, it's going to cool and cool and cool. And we're going to cool at constant partial pressure until we hit the dew point temperature. In other words, it's the temperature at where PG exactly equals PV. That would be 100% relative humidity. And any cooling below that, that's where we get dew on the grass. And so if you think about this, think about the definition of humidity ratio, the mass of vapor divided by the mass of dry air in the mixture. That means what we're doing is until the dew starts to form, we're cooling at constant humidity ratio, cooling at constant humidity ratio. And then if you think about the derived formula for humidity ratio in terms of partial pressures, you can satisfy yourself that that means we're cooling at constant partial pressure on this isobar line until we reach 100% relative humidity. So it's a little bit of a crash course on dew point temperature and partial pressures. And now we're going to get right into our example problem. So that took about 4 minutes of getting up to speed. Okay, outside conditions in Blacksburg are reported by the Weather Channel as shown over here. Determine the dew point temperature, because the Weather Channel isn't reporting. They could calculate it, but they're not reporting to you at what temperature will the dew form at night when it's cooling. I'm going to show you how to do this. All right. So the first thing we do is we need to look up P sub G, the saturation pressure at 16 degrees. So we'll go to our temperature table, H2O vapor, and we're going to see pressure in bars is 0.01818. Okay. When we write that down, remember, we need to deal in kPa. And so what we're going to write down is 1.8 kPa. That's a very low partial pressure, P sub G, at 16 degrees C. So we'll write that down. So here's our temperature, 16 degrees C. We wrote down P sub G, 1.818. Now we have, from the Weather Channel, we've got 69% relative humidity. We'll write that down. And so remember, the definition of relative humidity is PV over PG. Let's solve for the partial pressure of the vapor of our air. It's 0.69 times 1.818, or 1.254 kPa. Now, if we go back to the TS diagram, we think about cooling at constant partial pressure, what we need to do is we need to look up P sub G at 1.254 kPa, and that'll give us the dew point temperature. And so just by observation here, so we're going to look for our pressure, 1.254. I see it's in between these two. So before we do any math, we're going to observe that the dew point temperature is between 10 and 11 degrees C. If you're taking a quiz and you don't have time to do the interpolation, write this down on your page. The dew point temperature is going to be between 10 and 11, and you'll get some partial credit for that. Okay, but we have time to do the linear interpolation. So here's our interpolation table. Here is our P sub G. So we're going to linearly interpolate between 10 and 11 to get the dew point temperature is 10.31 degrees C. Now, many students will say, well, why don't you go to the pressure table to get these? Instead, why are you using the temperature table? The answer is that the pressure table does not have enough precision in these tiny little partial pressures for you to get a good, accurate result. So that's why you use the temperature table in doing this work. So our dew point temperature, 10.31. So we'll write it out in a sentence. The dew point temperature for 16 degrees C and 69% relative humidity is 10.3 degrees C. Practical conclusion. As the night goes by and it gets colder and colder and colder at night, if the temperature of the grass gets below 10.3 degrees C, let's say it gets 10 degrees C, you're going to get dew forming on the grass. Condensation will occur out of the atmospheric mixture. Condensate will form in terms of droplets on the grass. Next example, exactly the same example, except let's use the psychrometric chart to see if we can solve this problem any faster. And the answer, we're going to be able to go even faster for a solution here. 16 degrees C, 69% relative humidity. We'll go to the back of the book. We'll find our psychrometric chart. First step, determine where we are on the psychrometric chart. All right, we've got a dry bulb temperature of 16. Oh, dry bulb. Here's my thermometer. Here's the bulb of the thermometer. It's dry. So that's why we call it the dry bulb temperature. It's 16 degrees C. I'm going to be somewhere on this vertical line. 69% relative humidity. We've got to look. Oh, here it is. I see these parameters on my chart. Relative humidity, 10, 20, 30, 40, 50, 60, 70. I'm nearly 70, and way above 60. So I'm going to have to put a dot. I have to use my calibrated eyeball to put my dot, and in this case, I put a big old dot close to 70, nearly 70, might be a little bit low, but anyway, you get the idea. I'm going to put a big old black dot where my point is. Then how do I determine the dew point? Here's how you do it. I did all that talking about dew point and TS diagram, and I tried to convince you that we're cooling our mixture at constant humidity ratio. On the TS diagram, we were cooling at constant partial pressure, but if you think about the definition of humidity ratio, 0.622 times PV divided by P system minus PG, we're cooling at constant humidity ratio. That means on our psychrometric chart, look at the y-axis, humidity ratio. So we're cooling along a horizontal line. So here's our point. We cool along a horizontal line. And now look at this axis, wet bulb or saturation temperature. Those are wet bulbs. So that says dew is forming on the bulb. Okay. And sure enough, we look across here and I have to use my calibrated eyeball to carefully see that I'm going to say, for using my psychrometric chart, I've got a dew point temperature of 10.5 degrees C. You see how I did that? So this is can be a confusing chart. Lots of numbers, lots of lines. There's an x-axis, that's our starting point, dry bulb temperature, y-axis, humidity ratio, and then there's a bunch of other axes drawn in there too. You got to get some practice at finding this. All right. So that was our second. So using the psychrometric chart, 10.5 degrees C. So let's compare results using the two methods, both of which are perfectly valid. Both methods are perfectly valid here. So we use the steam tables to get a dew point temperature of 10.31 degrees C, about the best we could do with our calibrated eyeballs on the psychrometric chart, 10.5%. They are very comparable with each other, right? So don't get excited if you see, oh, they don't match each other exactly. Of course they will not, because the graphical approach doesn't have the same significant figures as the steam table approach. And so that's it. We've spent 12 minutes reviewing the definition of dew point temperature, gone through a couple of ways to determine the dew point temperature for a real world example. So you need to, in recap, need to understand the meaning of dew point temperature. What does it mean? What's the physical meaning? Now you know how to use the properties table by way of interpolation in the temperature table to get the dew point. And then if you use a psychrometric chart, about the best you're going to get is 3 significant figures. But both of these are perfectly valid ways to determine the dew point temperature of atmospheric mixtures. Okay, I hope that's helped. In particular, I hope that's helped you get started reading the psychrometric chart and solving problems, because I can predict that you're going to be asked to do that in a quiz or test situation. So good luck, and I look forward to your looking at the third in the series of psychrometric calculations.